In section 2.4.1, we're going to talk about another extremely important concept that you will consistently see throughout this class as well as subsequent calculus courses. So this is going to be the concept of continuity. So our goal here is to ultimately kind of describe a function as being continuous. And we want to say that a function is going to be continuous in this kind of loose sense. So when we say that a function is continuous, we kind of mean that this would be the type of a function that we could draw the graph of without having to pick up our writing utensil. So let me go ahead and try to just sketch out maybe a couple quick pictures of some functions that would be continuous, and then functions that would maybe not be continuous. So if I'm going to use this kind of loose understanding of drawing the function without picking up the pen or the pencil, I could create a couple pictures maybe like the following. So let me go ahead and draw a couple different possible functions over here. Here's a simple one, right? Maybe this is like a cubic function, right? But notice I could draw the whole thing without picking my pen or pencil up off the page. I could do a whole bunch of crazy sorts of pictures here. Again, I just have to keep in mind that they need to be functions, so I can't do any weird loops or any time where a given x value would have multiple y's. But I could do all sorts of crazy things, right? Like something, well, maybe not like what I did right here at the end, but I could do something kind of like this. I could go straight lines and then back like that and like loop around. Like this here, also completely continuous. And of course it is a function as well. So how could I maybe draw a picture where I would not get something continuous? What would that look like? Right? If I drew a picture where I did pick up the pen or pencil, then I might be able to create a picture that maybe looks something like this. Notice in order to draw a picture like this, I have to actually pick the pen or pencil up off the page. And so this is a graph that is not going to be continuous. Here's another example. I could go ahead and maybe think about something like this. Maybe I have a graph that has a hole in it somewhere. Maybe it goes like this and then maybe jumps down here and goes over, right? So here's a graph, not continuous. I can't draw that picture without picking the pen or pencil up off the page. Now, it's important to understand that when we use this word continuous and we talk about it as being a function I can draw without picking up the pencil, that's like a loose definition. It's not the exact definition. It's kind of like how in a chemistry class, and maybe you've taken a chemistry class before, you describe an atom and the electrons and electron rings, and you often tend to draw a picture that looks something like this, right? You say like, okay, so like here's like a nucleus, and then there's like, 2 electrons on the first electron ring, and then you draw another one, and you can start to talk about different elements and different bonds that begin to get formed, but in this whole process, is this what an atom looks like? Well, no, but it's kind of a good way to start thinking about the idea. And so in the same way, what we have here is a good way to start thinking about the idea of what it means for a function to be continuous. That I can kind of draw it in one smooth kind of connected motion, whereas with things that are discontinuous, I can't. Now again, that's not the exact definition, but now we'll present what the actual rigorous definition is. And here it is. A function f will be continuous at a specific number. So at a specific x value, it will be continuous if it's the case that the two things on either side of this equal sign are actually equal. Now notice what this tells me. This says that I need the limit of f of x as I approach a to actually be equal to f of a. Now, if you take a look at kind of what this means, we can see, again, that when we talk about the limit as x approaches a of our function, we're talking about what the function, or what y value the function leads us towards. Right? That's what we're really looking at here. Whereas when we talk about f of a, we're talking about the y value of the function at x equals a. And we want to check if these two things are actually equal. So technically in this definition, there's like a question mark above this. This is something that needs to be checked. So notice that in a picture like this, we can see that if we followed the blue path, we would be led towards this point right here, this y value. And when we plug in the value of a, we actually get the same exact y value. So it's at exactly these moments when the limit and the y value of the function produce the same value that we say that our function is continuous. So if you take a look down here at example number 1, we can start to see really quickly how we would answer a question like this. So let's take a look. Would you say that the function g, pictured here below, is continuous at the x value of 5? Notice what that means I would have to check. I would need to check the limit of the function as I go towards 5 and the y value of the function as I go towards 5. Well, notice here that the limit as I move in this direction is actually going to kind of be based on where this path is going to be leading me. And it looks like I'm being led towards this y value. So let's put that over here on the picture. This would be the limit of g of x as x approaches 5, right? So I don't know what y value that is. Maybe it's like a y value of 1. But I can easily see that the y value itself, g of 5, is going to produce this dot, and that has this y value here. So we can say that we see from the picture, that the y value that I'm getting back from my limit is definitely not equal to the actual y value of the graph. So we can say g of x is not continuous at x equals 5. These two values didn't come out the same. Even though we don't know what they are, we can clearly tell they're not the same y value. So in this sort of way, we can kind of get the sense that if continuous means that we need the path to actually lead us to where the actual dot or point for the graph actually is, we need those to match up, then we can see that pretty much any time our picture breaks apart into multiple pictures or kind of separates, that we're going to have a function that's not continuous. So take a look here. We could ask, what are all of the different values of x where this function is not going to be continuous? We've already seen that g of x is discontinuous over here at 5. There's a problem. Where the path leads us is not where the dot is. The graph no longer looks connected, so it's not continuous. Well, we can see a lot of other spots where this is going to also be a problem. So I'll say that g of x is discontinuous, and here are just a couple of the points. You might have already spotted some. Take a look at x equals 1. At x equals 1, the path is leading me towards, it looks like almost the same y value as what was over here. But where is the dot? Where is the actual point for my function when x is a 1? Well, we'll notice there is no point here. So that would mean that the left side here has some value, but the right side has no value, and so there's no way they could be equal. So x equals 1 is a problem. The graph's no longer connected there. We could also see that at the value of 3, there's a problem, because the y value is actually down here, so I could get something for this right side. However, When I take a look at the limit, notice that the path is leading me to a negative y value down here, but to a positive y value up there. So in this case, my limit would not exist. And so there's no way that these two sides could match if the limit doesn't even exist to begin with. So 3 is a problem. And of course, we've already mentioned that 5 is a problem. So this is kind of the idea of continuous, and we need to have a couple important takeaways here. First, it's really useful to understand this loose idea that continuous means that we could draw a picture without picking up the pen or the pencil. We should also have that connected in our mind to the idea that a continuous graph or a continuous function will look like a graph that is all connected. And if I ever see disconnected pieces in a picture, like empty spaces or gaps or jumps, then I know that my graph would be discontinuous. But if I ever wanted to show rigorously that a function was continuous or discontinuous at a point, I have to double check the limit and the y value at the x value in question.